Okay, so let's just get started. Class will hopefully increase in size. Extra points for everyone who showed up. All right, so couple announcements. We have our exam next week, and I do plan to make another of the study guide available like I had done for exam 2. So I haven't made it yet, but sometime this week I'll put it up so you have about a week to use that to prepare for the final exam. Okay. Again, final exam next Friday, May 19th, 1 o'clock. Okay. Then Marcus Hall, and I'll send out an email with all the details. All right. So let's continue from last time. We had a couple slides remaining on file systems at the very end of the class. I'll cover that. And then for the rest of this class, we'll talk about middleware system. Okay. So we were talking about HDFS. That's the Hadoop file system. Okay. It's a different file system from a traditional general purpose file system where you can use it to create files, edit files, and so on. This file system is specifically designed for large scale data analysis. Okay. So it assumes that file sizes are very large because the data sets could be gigabytes, terabytes in size, and you want to use those files to process data using Hadoop. Hadoop uses a map-reduce architecture, which I'm going to actually talk about hopefully in today's lecture if we can get to that part. All right. So the basic ideas in HDFS are twofold. One is that there is a separation of data servers and metadata servers. Okay. In earlier file systems we looked at, we didn't make a distinction. The server stored data and also the metadata for the file. There was no distinction. In this case, as the file systems start growing in size in terms of the amount of data they store, certain machines in the file system are dedicated to serving metadata, okay, which is where the content lives and so on. And the reason is there is enough load in the system that it is better to put the metadata on certain dedicated nodes, and the other nodes are data nodes. Okay, so here the blue nodes there's only one shown in the picture, but the blue nodes are metadata nodes, and the yellow nodes are data nodes. So if you want to look up a file, okay, either read it, write it, open it, you first got to go to one of the metadata nodes and open the file, and also look up where the chunks of the file are stored, and then you go to the yellow nodes to look for it. So essentially the index is on the blue node and the other things are on the yellow node. Okay. That's one. The other important aspect to keep in mind here is because the files are large and you basically have optimized this for a scenario where you create the files, there are large data sets, but they're read many, many times. Okay. So it's write once, read many type scenario. But more importantly, unlike RAID, which we talked about last time, we are not going to stripe the files across nodes or anything. That could have been one architecture. That is not what is done here. Instead, you simply take the entire file or every block of the file and replicate it a few times. Okay? Typical replication factor could be 3. You will see that the number of replicas here is shown for food data is 3. That means that file is replicated 3 times. It's kept on 3 different machines, or chunks of it are kept on 3 different machines. Okay? So that's the basic idea in HDFS. And next we are going to look at the Google file system, GFS, which is also designed for large-scale data analysis. Similar ideas, okay, in both file systems. Okay? So both of these file systems are not traditional file systems that you're going to see on your desktop or laptop, that you're going to open files and edit files or anything like that. They're designed for very large data sets. Okay? So this one also has a master-slave type architecture where the main node essentially is the metadata node. So the separation of data and metadata that I just explained in HDFS also present in GFS. Okay? Some nodes are essentially metadata nodes. So you'll see that there's a file system namespace, that's your file system tree, and for each file you keep a table saying where is the first chunk, where is the second chunk, where's the third chunk. Okay? And so that's going to tell you which machines is stored on. These are the machines that are actually your data nodes. They're called chunk servers. The reason is you take a large file, because files could be terabytes in size. You chop it up into chunks. Chunks could be large. They're not like data blocks of a file, which are 4 kilobytes in traditional file systems. These could be megabytes in size, okay, the chunks. So you take the first chunk, you put it on one of these machines, okay? And that chunk is actually stored on the machine as a normal Linux file, okay? Because you are essentially layering GFS on top of a standard Linux file system. So a chunk server is just taking a large chunk and storing it on its disk, and then another chunk is stored on the another machine, and so on. And just as in HDFS, we essentially said you have a replication, same is true here, okay? All files are replicated by default 3 times, okay? That means you need 3 times as much storage space, okay? Remember when I was talking about RAID, I said mirroring just reduces your storage space in half. And we thought that was expensive. Now, in modern large-scale file systems, they replicate it. In fact, there's a replication factor of 3. That means the actual storage space in the system is 1/3 of the total storage, because everything is, there's 3 copies of everything. Okay? You don't use parity or anything like that. That RAID 5 used to simply replicate the entire file. This way, even if nodes go down, there are 2 more copies. If 2 nodes go down, hopefully there's still a copy remaining on the system. Okay? So that's how modern file systems have approached it. They have decided storage space is cheap, so you don't really need to do all of what we did in RAID and so on. Okay, so you can control the replication factor. At least in HDFS, it's a tunable parameter. In GFS, it's default set to 3, but you can change that in HDFS. You can make it 1, which means no replication, keep it 3, or increase it, and so on. Okay, so that's our GFS file system. Only a quick overview, of course, it's only one slide here, but something to keep in mind. These are modern large-scale file systems for data analysis. Okay? And the last thing I want to say here before we switch to distributed middleware, which is today's topic, is object storage systems. Okay? Now, I don't know when we did the cloud lablet whether you used S3. Did you use S3? Yes? No? Can't remember. Didn't use it. S3 stands for Simple Storage Service. Okay, there's 3 S's. That's just why it's called S3. So S3 is Amazon's object storage layer. Okay, and the reason I mentioned this is object storage systems are different from file systems. You all know what a file system is. Okay, how it works. Your files are organized into directories. Directories can have subdirectories and so on. Okay, object storage systems are different. Okay. First of all, like HDFS and GFS, object storage systems are also designed for larger scale data, not necessarily small files that you store in the files. Okay, that's first thing. Okay? Now, the main difference between object storage system and file system is you essentially the chunk, whatever you store, is now referred to as an object, not a file. Okay? And objects don't have file names. There is no hierarchical namespace. Every object is a container of data, and it has a numeric handle. Okay? The way you are going to access that data is through that numeric handle. Okay? That's the first thing. And the second difference between file system and object storage system is in file systems, you have reads and writes to access your data. Okay? In object storage systems, your gets and puts. Okay? Get allows you to get the entire content. Put allows you to put data into that container. Okay? Now, so you have essentially gets and puts. You can use HTTP, okay, as a way to do gets and puts rather than doing file reads. You can essentially use HTTP as the way you are going to access this storage system and then use this type of API to access it. So essentially, the way you want to think about it is no hierarchical structure. Okay? Each object, okay, in S3, it's called a bucket. Each object is a large container of data. You can put whatever data you want in it, but the way you are going to access it is you need the handle, okay, which could be a HTTP handle or it could be a numeric handle. But you use that handle, you get to it, the container, and then you are going to access this data using a get, or you can add more data using a put. Okay? So, and it is mostly used for things like archival storage. This is not designed for high throughput operation. Okay? You are not going to use this to run some a high-end database or anything like that, because the whole storage system is designed not for high performance. It's designed for large scale and large sizes and things of that sort. Okay? So, and internally, S3 actually also, like GFS and HDFS, keeps 3 copies of every object. Okay? You don't know it. Okay? You are just going to go and say, give me this object. It can go and find one of the replicas and get the object for you. Okay? So similar concepts, but not using the abstraction of a file for large-scale data access. Okay? Any questions about object storage systems before I move on to distributed middleware? Okay, so let us now switch gears, go back to today's lecture. Okay, so what we will do now is switch gears and talk about middleware systems. Okay, so remember, in the very first lecture, I said middleware is a software layer that's going to sit between the operating system and the application, and it provides useful services that the OS does not provide, that the application can make use of. Okay? So now we are going to look at what these middleware systems can do for us, how they are used in practice, and so on. So we are going to look at 4 different middleware systems. Okay? Enterprise Java Beans, which are also called EJBs. Okay? Then we are going to use DCOM, which is now called .NET. Okay? That's Microsoft middleware system. We'll look at an old one called Corba, not used anymore, but it was one of the older ones. It's good to understand a little bit about what it does and why it has not actually caught on. We'll then talk a little bit about a different middleware system called Genie. It has a very different flavor. It uses something called a blackboard architecture. Again, something we had covered in lecture 3. That point I said we'll come back to it. So today we do have opportunity to come back to it. So we'll look at that. And then if we have time, we'll start talking about Hadoop and Spark, which was essentially what HDFS is, the storage substrate for some of these distributed data processing systems. Okay, so very quickly, distributed objects. We've seen this picture many times now. Okay, there's a client and a server. Okay, the client has some code that can make requests, okay, RMI calls on an object. So the object now essentially lives in a process on the server machine. Its methods are now exported and can be invoked as RPCs or RMI calls. Okay? And we have stubs, which are called proxy and a skeleton in the object-oriented world. So we've already seen this picture. Okay? Keep this picture in mind. Now we'll see how you can use this very basic concept to build higher level services in middleware systems. Okay? The first one is called Enterprise Java Beans. Okay, so you all have maybe used Java as well already. There's a version of Java called Enterprise Java that's used to build all kinds of distributed applications. It essentially is a superset of what standard Java is going to provide. The question is, what other functions does it provide? So you will see that it's essentially a middleware service. So it's going to have these extra services. RMI already present in standard Java. So you already use that if you use Java to write any of your code. Okay? And there's something called JDBC. That's essentially the Java module that allows you to connect to databases. Okay? So that's essentially your Java database connector. Okay? Then there is JMS, which is our messaging service. And there is JNDI, and I've even forgotten what that means. But it is those are all services. But what we want to actually look at are these boxes called EJBs that are sitting at the top. Those are objects like any other Java object. So you have classes, and you instantiate a class, you get an object. Okay? Even in Enterprise Java, you're going to have objects. But unlike standard objects you have in Java, these objects have specific features. Okay? And let's look at what EJBs and other types of objects can provide us. So first thing you want to keep in mind is, like any good object-oriented programming language, EJBs and Enterprise Java require you to declare the interface for an object, because all of these objects are going to have RMI features. So you declare your interface, and that's your remote interface. That's essentially what you're going to export to applications. Okay? Client-side application. Okay? And the assumption is EJBs are used to build distributed applications like web services and all other kinds of applications. So essentially the EJB code, the class, encodes the business logic for the application. It's essentially the application tier of whatever application, your distributed application you're building. Okay? And you essentially have then the object itself, which has the code for whatever the interface is actually exporting. So here is a quick summary of 4 types of objects you have in enterprise Java. Okay? So this, unlike your standard object in Java, here you have 4 different types. Okay? So first is whether your object has state or no state. So you can have something like a stateless object called a stateless session bean. So you, in this case, the object is created for the duration of a session. Just as you had a thread per request model, when a request comes in, okay, you essentially instantiate an object, instantiate a thread. So then the method is of that object is going to service that request for you. Okay? And when the request is done, because it's stateless, you're going to throw it out. Okay? You essentially terminate the thread, terminate the session. Okay? So the lifetime of the object is the lifetime of a request in this case, or the session rather, not really a request. Okay? And so you can have 2 kinds of these session beans. One is stateless, which means there's no state in there. Another one is stateful. You can keep that state. Multiple requests within the session can see that state. So for example, if you have an e-commerce application, okay, your shopping cart could be an object. Okay, so when you start browsing, you put requests into the or products into the shopping cart. All of that will be state of the session. Once the user is done browsing and maybe they've purchased whatever they want to purchase, this object is going to be thrown out, and the thread that was associated also terminated. Okay? So this, so now what we have done is, rather than just instantiating a thread, we instantiate a thread and an object for every session that is coming in, and that object is responsible to provide the code for servicing the request. The thread is essentially executing that code. Okay? So that's your session bean. Okay? The other type of bean, and bean is just a type of an object here. Entity bean, which is really the more fundamental part of EJBs, is essentially a persistent object. Okay? Here, the object has state, and furthermore, that state is stored on disk. Okay? So you can think of an object that has all kinds of state in it. Maybe there are records, there are variables. All of that is actually stored on disk. So whenever you can update the state, and then it will also update the disk version of the state. So what this also means is enterprise beans are objects that live beyond the process itself. Okay? Your process can be shut down and restarted, and then it can just read the object back from file, and it reappears as if it has always been in memory. Okay? Normally, your classes and objects, they are essentially part of the memory state. So if your process crashes, all of that is gone. Okay? In this case, you're saving your entire object on disk. Okay? And this is essentially fundamental to entity beans, because you're going to persist that state on disk. Okay? So that's very different from whatever you might have seen in Java, except if you use serialize, deserialize in Java. If you serialize an object, you can take the object and put it on disk, and you deserialize it, you read it back, and you recreate it. All of that is automatically done in a entity bean. Whenever you keep changing its state or change any aspect of that object using methods, you keep saving that state. So you can always deserialize it at a later time. Okay? So those are entity beans, and the last one is message-driven beans. So these are used more for messaging. There are things like message queues that can also either live in memory, persist on disk. You can send messages, but these messages can live beyond the duration of the process itself. Okay? So 4 types of functionality. Okay? I'm not going to spend too much time on this. I just wanted to give a flavor of how some of these middleware systems are going beyond what you might see in Java and things like that. Okay? Any questions on this? Okay. So let's talk about another one. This one is called Corba. Okay? This was one of the earliest large-scale middleware systems. Okay? So the idea here was to develop a middleware layer that could provide all kinds of useful services to applications. So you would not, as a programmer, have to write all of that code. Okay? So you will see here that there are things, there's something called common object services, there are domain specific services, there are general purpose services, and this is your application code. Okay? That's on the leftmost box. And all of this is going to communicate through an RPC mechanism, but the RPC mechanism uses something called an object request broker or an ORB. And that is why you have that name Corba, because it's common object request broker architecture. Okay? So your ORB is your messaging layer that allows applications to access services, services to access other services, and so on. So all of these services and the ORB layer, which is the communication layer, is part of the middleware. You just write the application code, which are essentially objects, and they can access all of these services. That's the architectural view. Okay? Now let's talk a little bit about what these services are, what they can provide for us. Okay? So, and the way you can do this, write applications, you install a set of services, write a set of objects, and then use those services. Okay? So here's a list, okay, of all the services that Corba is going to provide. And what you will see is Corba is now a heavy-duty middleware system, provides all kinds of services that you might think of. So there's one called a query service. If you want to query a database, you can use the query service. There's a concurrency service. So if you want to do threading, you have a concurrency service. There's a transaction service. You want to implement transactions in your application, you just use transaction service. There's an event and a notification service. Okay? If you want to sell your code as a commercial software, there's a licensing service. Okay? There's a persistent service. If you want to encrypt data, there's a security service. Any possible thing you can think of that you might want to put into a large-scale application, they made it a service. Right? So you could just use those methods of the service and get that functionality. So you don't have to write it yourself. Okay? So the good thing is a lot of stuff is already in the middleware. You just have to know what services to use. Okay? The not so good things is that this has become extremely heavyweight. Okay? If you want to write even a small application, you might have to have all these services running. It actually increases the overhead of even running small applications. Okay? And it increases the complexity of using the middleware. Okay? So although the designers of Corba had good intentions in terms of saying, okay, we can think of all these types of functionality that a distributed application developer might need, and we make that a service, okay? They essentially went too far. Okay? They put so much functionality into the middleware that the middleware itself became very heavyweight. So it never became a commercial success because it was very slow, okay, to run, and there was a lot of overhead for running it and so on. So you don't actually see a lot of Corba-based applications that ever got built or deployed. There are a few systems that still used a stripped down version of it. One of them is actually, if you use Linux, and you know that there are different desktop managers in Linux, there's one called GNOME. Okay? That's the GNU network manager. So that actually is built on top of a lightweight version of Corba. That is probably the only large-scale system out there that still uses it, but this never actually took off because it was too heavyweight. And other lighter weight versions of this actually got built eventually and used in different applications, one of which was EJBs. Okay? Corba came maybe 2 decades before, or maybe at least a decade before EJBs. Right? So that's Corba. There are some other features of Corba that I also wanted to mention. So this is the object model in Corba, and as you can see, this looks pretty much like any other RMI RPC system. The ORB is acting like a stub. Okay? You essentially have an interface definition language that you use to define your methods. Then you have an IDL compiler. You compile it and it's going to generate the stub for your code. Then you write your application client and server code. You link it to your stub and you get a client version of your application. You get a server version of your application. So that part is no different from any other object-oriented language. It's just that you would then have to figure out using your RPCs or RMIs which services you are going to invoke and things of that sort. Okay. Now, Corba had many features where you could actually dynamically decide at runtime what object you are going to call, dynamically import its method. So you don't even need to know when you're writing the code all the methods that a object exposes. Okay. At runtime, you can say, I want to access this method. Corba will go and fetch its interfaces, put it in your stub, and then you can actually, your code has to then figure out which of these methods can be used. So that's essentially dynamic invocations of interfaces. You will not see that in normal object-oriented language, right? So when you write the code, if you write a RPC call, you need to know what the method name looks like, what the arguments look like. You're not figuring that at runtime. You do that as essentially when you write the code and compile. Okay? So Corba has all these advanced features where you can also decide these things at runtime. Okay? And if you remember when we were talking about RPCs, I mentioned that you can have synchronous RPCs, one-way RPCs, deferred synchronous RPCs, and so on. Okay? Corba supports all of those models. Okay? When you make an RPC request in Corba, you have to specify this is a synchronous call where the client is going to block and wait for an RPC reply. Okay? Is it a one-way RPC where you just send the RPC, don't wait for an acknowledgement? Okay? Is it a deferred synchronous RPC? Is it an asynchronous RPC? So all of these actually came from Corba. They were the ones who decided there are different ways to invoke an RPC call. The standard blocking synchronous one is not the only. Okay? So that's supported here. And we had already looked at that when we talked about RPCs. Okay? The other interesting part of Corba is that built into it is a publish subscribe model, okay? Which is an event and a notification service. Okay? So this is the first time we are seeing a pub sub model. Okay? Let me explain what a pub sub architecture is, and then we'll see some ways Corba allows us to implement. Okay? So the word publish subscribe, as the name suggests, okay, essentially means that communication between two entities is going to take place not using things like standard RPCs, but by publishing events and subscribing to events of interest. Okay? So we have two entities in this case. Rather than a client and a server, your publishers and your subscribers. Publishers produce data. Subscribers consume data. Okay? And the way publishers and subscribers communicate is the publisher doesn't say, here's a data item, deliver it to this client. That's not how it works. What you're going to do is publisher is going to publish data and say, these are the characteristics of this data. The subscriber should have subscribed to certain types of data. Say, I'm interested in these types of events, okay? Or I'm interested in updates on these types of events. So whenever a publisher publishes something new, there is some intermediary, which is our middleware. In this case, it's called the event channel, also sometimes referred to as an event bus. Okay? The event channel or the event bus responsibility is to deliver the events published by the publisher to any subscriber that has an interest in that event. Okay? So here we have publishers, which are called subscribers in this figure. They are producing data. The data goes and sits in an event bus. Think of this as a big buffer. Consumers are subscribed to events at a certain type. Whenever new events come, you look at the subscription list of a client and say, does this event match anything this client or any of these clients need? If so, you are going to deliver that. And if not, you just keep it buffered. Okay? So this picture on this slide shows us a publish subscribe model where rather than clients and servers, you have publishers, which are processes, consumers, which are processes. They are not using standard RPCs, RMI, or any of these methods to communicate. It's a pub sub model. Okay? And furthermore, as this picture shows, this is a push-based publish subscribe model where the publishers are pushing data to a event channel, and the event channel is pushing data to consumers. Okay? Push and push. Okay? And Corba also supports this. This was actually one of the first time they implemented this in middleware. So if you want to use a pub sub type application, all of that, you just have to use the event service from Corba and you get all of this functionality. Okay? Now, there are other ways to do this, which Corba also supports. So here is a pull-based approach. Okay? So the event channel is going to periodically ask publishers, do you have any new events or new data to publish? Okay, so event channel is polling the publishers and pulling data into the event channel. Okay, and consumers are polling the event channel saying, is there any new data that I've subscribed to? Okay, so and then based on whatever you're subscribed, the event channel will deliver that data to the right application. Okay, so this is our pull-based model. Now, of course, you can combine push and pull, where the connection between the publisher and the event could be push, and the one from the consumer to the event channel could be pull, or any combination thereof. Okay, so I showed push, push, and pull, but you don't need to just go with that. Okay. Any questions on pub/sub? All right, so there are two more things to keep in mind here. The one is you can use essentially a callback model for asynchronous method invocation. So remember, I said that Corba supports all different types of RPC invocations. One of them is asynchronous RPCs. Okay? If you remember a long time back when we talked about asynchronous RPC, you said you send an RPC request. Okay? You no longer block. So you just send it and the client continues execution. The reply is going to come back at a later time. Okay? Since the client is not blocked, how does the client know the reply has actually come back from the server? Okay? There are two ways to do this in Corba. Okay? One is you have a callback. Callback essentially says, I send this request, and when the reply comes, the stub is going to essentially call the callback function, which is then going to tell the client saying your reply has arrived. Okay? So this is essentially the callback function, and you will see that in this case, there's a callback interface that the client has registered. When the reply eventually comes, it comes because it's asynchronous. You go to the callback interface, you make a call here, and then the application is notified. Okay? So the callback is a way to notify the application that the reply to your asynchronous RPC has arrived. Okay? That's one approach. The other approach is essentially polling, okay, where the client again is using an asynchronous RPC. It made a request to the server and it continued execution. But periodically it's going to check, has my reply come? Okay? So that's essentially you're going to use the polling interface where you'll periodically poll the stub saying, has the reply arrived? Has the reply arrived? Eventually the reply would have arrived, and then you're going to take delivery of that reply and process the results of your RPC. Okay? Both of these are approaches where you can use asynchronous RPCs, but not have to wait for the response and then get back a reply, either using callback or polling. Okay? Is that clear? Any questions on this? Okay, so that is Corba's asynchronous method invocation. Now, having talked a little bit about Corba, I'm going to switch to a different middleware. It's called DCOM and .NET. So this is essentially Microsoft's middleware systems. Okay? So DCOM essentially is again an acronym that stands for Distributed Component Object Model. Okay? Again, an object-oriented framework. Okay? It has evolved over time. I'm going to give you a little bit of history. DCOM has now evolved into .NET, which is now used with C# and all other kinds of programming languages. But it's good, instructive to understand how all of this essentially arose. Okay? So you will see here that there are three layers in that architecture. There's something called a COM layer. Okay? That's essentially a very basic RPC, RMI layer for objects. On top of that, you have something called OLE, which is called object linking and embedding. And then on top of that is ActiveX. So I'm going to say a little bit about each of these. Okay? So the way this all arose was essentially a need within Microsoft's Office framework for Office applications to communicate with one another. Okay? So if you can think about why Office applications need to communicate. Assume you are using PowerPoint. Okay? Now you want to, within PowerPoint, you want to embed a chart. Okay? Maybe you made the chart in Excel where you have some data, rows and columns, and you plotted some bar graph using that. You want to import that bar graph into Microsoft PowerPoint. Okay? So one way you do is you're going to cut and paste it, and then the picture has appeared in your PowerPoint. Another way to do this, you can link the spreadsheet directly into your PowerPoint application, and PowerPoint and Excel can actually communicate in the background and import the data and display it. Okay? Then you can go and change the spreadsheet, and your chart will automatically update in PowerPoint because the two are communicating. Okay? And similarly, you can think of Word. You try to take some picture that you've drawn in maybe PowerPoint, and then you want to import that as a picture into Word. So Word might want to talk to PowerPoint and so on. Okay, so in any case, those are simple examples that tell you that these applications have a need to communicate. So when Microsoft was developing Office applications, they've said we need these applications to talk to one another. Okay, so they said let's build an RPC framework that allows them to do that. Okay, that basically gave rise to essentially COM, which was the RPC layer. Okay, so objects which are pictures or whatever documents you have or spreadsheets essentially are exported as objects. You can call methods on them and so on. And then on top of that was object linking and embedding, which is OLE, that allowed you to do document linking. That is where you can import something from Excel into PowerPoint or export something from PowerPoint to Word and so on. And you can do drag and drop. You can do in-place editing. All of these features were supported using RPC call. Okay? And then on top of that, essentially, they put another layer, which was called ActiveX. Okay, ActiveX essentially allowed you to take all of this and export that as web applications using web servers and so on. So now you can have browsers connect to these applications, and then you can actually see documents in browsers and so on. Okay, so ActiveX controls essentially added some web functionality to this. Okay, so that was Microsoft's evolution over maybe 10, 15 years of why they wanted RPCs. They wanted RPCs not for Windows, but they wanted it more for Office. And then they allowed you to do object linking and embedding, ActiveX, and so on. Okay, so you take all of this, and this is still on a single machine, by the way, okay, because you are not having Word on one machine, talk to PowerPoint on another machine. That was not how it evolved. These are just processes talking to one another using COM. Okay? But then eventually you had to go across machines. That is where they took all of this and made it distributed. That gave rise to DCOM. Okay, I'm just giving a history of how all of this has evolved. And DCOM later on became .NET. Okay, so essentially you have COM, then which was simple RPC calls, object linking and embedding that allowed Office applications to talk to one another. So essentially ActiveX added web functionality, DCOM made it distributed, and then eventually they made it language independent using .NET and so on. Okay? So that is Microsoft's evolution of all of this. Let's look at some details of how some of this works. So if you look at the basic architecture, okay, although I said all of this came about from Office application and so on, you can use it to write any arbitrary application. It looks no different from a client-server RPC application. Okay? You will see there's a server here, which is your object server. That's the code for the object. Okay? You have essentially proxy marshalling, demarshalling of arguments. There's a stub. There's a COM layer that's actually going to send your request. Okay? And here is the client machine. Again, your stub, your application, and so on. Okay? So it looks very similar to all of our RPC object-based systems that we have seen before. Okay? Not very different. There are two things here. There's a type library that's equal to Corba's interface library. An object is going to register its interface with the interface repository. When the client wants to access it, you go and access it. So this is playing something similar to what a name server would do for us, except that you registered the entire interface, not just the name of the process into the registry. Okay? And then there is a implementation repository, which is called the service control manager. That is where the code of this object is essentially going to reside. So you will see that there is a SCM that's going to load the code to run the application. Okay? So that's a simple example of how Corba applications work. And just as we were talking about EJBs, okay, you will see that even here you have different types of persistent objects, non-persistent objects, and so on. And you have essentially a set of steps that you have to perform in order to bind to an object, send a request, and so on. So client is going to call bind to bind to a moniker. Moniker is just the name of the object. That's going to look up the object into the service control manager. You load the code for the object. Okay, then you create a class. Okay, and then you essentially, if it's persistent, you're going to go and load the state into the object. So now the object has been recreated. Then you are going to essentially make a request because now you have essentially recreated the object and its state from the service control manager. Okay, so you have persistent objects similar to what EJBs have. Okay, so that's the equivalent. Monikers are the equivalent of enterprise Java beans in the Java world. Any questions on this before I switch gears and talk about a very different type of middleware altogether, something we have not seen. All of this, we've seen the concepts. These are just case studies of how commercial systems implement them. Okay, so we'll talk now about a different type of middleware. This is called distributed coordination middleware. Okay, so to understand this, I will explain a few different ideas, and then we'll see what this type of middleware allows us to do. Okay, so if you think about the various types of coordination models, there are two ways to. There's a taxonomy you can think of that allows us to classify them across space and time. Okay, so you can either be coupled or decoupled in space, or you can be coupled or decoupled in time. And depending on which mode you are in, there are different ways for the client and the server or components of the application to communicate with each other. Okay, the simplest one is where you are both coupled in space or time. That's called the direct model. Okay, this is our standard client-server model. The client has to be running, the server has to be running at same point in time, and they have to be connected to one another using RPCs or RMI. That's the simple thing that you all know of. Okay, but there are three other approaches also that you can use. One is called mailbox coordination. Okay, so if in the mailbox coordination, essentially you are coupled in space but not coupled in time. So this is similar to how email works. Okay, when you send an email to somebody, you are not expecting that somebody is actively checking their mail. Okay, your mail is just going to go and sit in their mailbox, and the delivery of that message is going to be done at some later point whenever they check their mail. Right? So you can use this exact same concept for designing a distributed application. A client will send a message to the server. Okay? The message is going to go and sit into something called a message queue, which is a mailbox, it's a persistent queue, and the server can take delivery at a later time and process it. Unlike a standard RPC, you send a message, the server processes it, sends back a response. That's our direct model. Right? In the mailbox model, that's not, you are no longer coupled in time. Right? You're uncoupled in time, which means that sending and receipt are going to happen at many very different times. That's what uncoupled in time means. Okay? So that's another way of having communication between the client and the server. Okay? Yet another way, which is a third approach, is essentially meeting oriented. So this is our publish subscribe model. Okay? So this is like a meeting where you announce a meeting, and then whoever is interested shows up. You are not address the meeting necessarily to anyone. So you can just say, we are going to have a rally to celebrate this or to protest against something. And then you just post that, and you don't know who's going to come. It's not addressed to anyone. Say anyone who's interested in this can come. Okay? And then some set of people show up. Okay? Same thing is true here. In the publish subscribe model, when you publish an event, the publisher doesn't know which clients are present, who is going to take delivery, what subscriptions they have. You just publish an event. Okay? And then a client can take delivery of that event if they're subscribed to those types of events. Okay? So here you are essentially coupled in time. It means that both the client and server are executing. Okay, so the messages are flowing to the event bus, but you are decoupled in space, which means that messages are not addressed to any specific entity. Right? So that's meeting oriented. And the last one is essentially called generative communication, okay, where you are decoupled in space and time. So essentially, you can send messages, but not addressed to anyone in particular. The delivery of that message can be taken at a later time. So neither are messages addressed to any specific entity, nor is the delivery of the message going to take place immediately as soon as it's sent. It can be taken. You can take delivery at a later time. Okay? And this is what we are going to look at in essentially a distributed coordination model. Okay, this is something you probably haven't seen. It's not something we normally use in any of our distributed application, but it's an interesting way of designing application. Okay? So we are going to look at a middleware system called Genie. It's essentially a Java-based middleware system. It's also referred to as a blackboard or a shared data space architecture. Okay? So the way this is, so, and I may have mentioned this also when we were talking about this very briefly in lecture 3, in a blackboard architecture, so not really a blackboard, but a notice board architecture, okay, you essentially think about how a bulletin board works. Okay? You can go and post a flyer on a bulletin board. Okay? That flyer is not addressed to anyone in particular. It's about some topic, and there are many flyers posted. Okay? And then users come, they look at the bulletin board, they might see something of interest, some other flyers may not interest them, and so on. So they only look at information that concerns them. Okay? Now, and one example is maybe you are graduating, so you decide to sell off all of your furniture. So you make a flyer and you go put it on a bulletin board. Okay? You have no idea whether anyone is interested in buying what you are trying to sell or when they will be even interested. You just post it and hope that somebody is going to be interested and they will contact you. And you put maybe you put your phone number or your email saying, contact me if you want to buy my sofa or something like this, right? So this message that you posted is not addressed to anyone in particular. It's just a message of a certain type. In this case, you're selling your furniture. Okay? Now, when users are looking at this, they look at it at some later time. Okay? It's not like as soon as you post it, there are people standing there and they're going to look at it and contact you. It may be hours, days before somebody sees this flyer and contacts you saying, I would like to buy some of your furniture. Okay? So it is decoupled in space and it's decoupled in time because you didn't address the message or this flyer to anyone in particular. Neither are you expecting that responses will come at any given time. They can come at some arbitrary later time. Okay? So this bulletin board architecture uses this exact same concept that I mentioned of a physical bulletin board in sort of our distributed application. Okay? So our coordination model is a bulletin board. It's a virtual bulletin board, not a physical one. The applications are going to go and post messages or notices in this digital bulletin board. Okay? Other applications are going to come and query for certain types of messages that if they are present, they'll be returned to you. Okay? And then you will use that message to communicate between whoever posted that message and whoever has subscribed to that message. Okay? Now you can ask, how is this different from a publish-subscribe model? Isn't it the case that in a publish-subscribe model, you publish some event to the event channel and then you subscribe to it? Isn't the event channel a bulletin? Okay, subscription has to be done beforehand. Yes, so subscriptions in publish subscribe are done beforehand. Second is, as soon as the event is published, it's not stored for a large amount of time. You look at the subscription, you deliver it, you're done. Okay? In this case, you publish something, there are no subscription a priori. Your flyer can store, say, on the bulletin board for days. Same is true here. Messages you post to this bulletin board, which is called a Java space, they can be there for a long period of time. Okay? And then you can go take delivery of it. Okay? So let's try to think about, I mentioned in the physical world that you use bulletin board, maybe you want to sell your furniture. What application could we write with this type of system? Okay. So you can announce services and go look for services. So one example of this architecture is where you can announce a set of services that are present in the environment and users come looking for service. So what services would you like to announce? So let's take an example. Let's say that maybe in your house, you have a printer. Okay. Now, normally the way you access the printer is on every machine that wants to access it. You are essentially going to have to configure the printer and then you print to that printer. That's how you normally do printing. Okay. But in this model, your printer is simply going to make a post to the bulletin board saying, I am a printer, I offer a print service. So I'm a HP model printer of whatever, some model and so on. And here's my IP address. Okay. Now, if some device enters your environment, maybe then it wants to look for a printer, it is going to query the bulletin board, is there a printer in the environment? Okay. And then you find a printer. And you say, okay, that's a printer. I'm going to then use that printer and send it a print job. So I have not pre-configured the printer on my device. I go discover that printer and then I print to it. Okay. So the example I just described is called service discovery. Okay. So a popular approach where you don't have to pre-configure a set of services. You just publish their presence and then you can go discover them and use whatever service you want. This is just one example. You have a printer service, but maybe there are other devices. There may be sensors in the environment saying, I'm a temperature sensor. Okay. So if you want to now look for a temperature in the room, you go and say, is there a temperature sensor? And then you go look for it, and then you can read what the current temperature. So you can advertise all kinds of services. You can use the bulletin board to discover these services on the fly. You don't need to know that they are present. Okay. You can just go discover whatever you want and then access those services. Okay. So this type of approach is popular for essentially accessing services without pre-configuration. Okay. If you knew what services you wanted, you can just pre-configure them and say, this is the IP address of the printer, this is the IP address of the temperature sensor, just go access. But many times you don't, and this is how you're going to deal with it. So this model is very useful in those types of environments. Okay. So those are examples. Now let's look at some details. In the Genie case, our bulletin board is essentially called a Java space, but it's basically a database. Okay. It's a distributed database that's going to store tuples, and I'm going to show you some pictures here. So here you can see now you have this Java space. There's a publisher that publishes it. Subscriber comes later. Okay. Unlike a standard pub/sub model, this essentially is a bulletin board where these data items are going to be stored and for long periods of time. A subscriber can come and query and get notification. This is not our standard event channel based pub/sub model. This is a bulletin board based model. So here's an example of how a Java space can work. The three applications at the top, this dotted thing here is essentially our bulletin board, the Java space. So that's a service. It's going to write something called A. Maybe it says I'm service A. Okay. Here's another one that says I'm service B. Okay. This Java space could be replicated, which is why, although this is a logical thing, you will see there are 2 copies of A, because there may be multiple physical instantiation of these databases. Okay. And then here is a application that comes along at some later time. Okay. And it essentially says, is there a tuple that matches something? In that case, maybe it's looking for something that matches C. If so, you can take delivery of C and delete it, or you can just read it and leave it there. Both options are possible. Okay. Just a note, you don't actually delete the service, you just read it and leave it. But if it's an actual message, you can take delivery and remove. Okay. That's an optional part. Okay. So that's how any database would work. So our entire bulletin board is implemented internally using a simple replicated database. Okay. So here are some ways you can actually implement other interesting things. You can actually request a callback saying, I am looking for a printer service. I don't see it now, but if some printer appears in the environment, notify me. Or I'm looking for certain types of sensors or services, notify me later. So rather than looking over and over again, you can tell the bulletin board, just notify me at some later time. So you could request callbacks as well in this model. Okay. And here are 2 ways you can do reads or writes. Okay. So you have essentially you can see now that there are 3 copies of the Java space. The bulletin board is replicated on all machines. Okay, so now when you try to write, okay, so one approach is you write to all bulletin boards. Okay, and when you read, you are going to read from your local bulletin. Okay, so a very easy way to understand it, maybe there is a bulletin board on each floor of a building. Okay, so if you want to post a flyer, you go and post the flyer on each floor. Okay, then users have to only look at the local bulletin board if they want to find some. Okay, so in this case, writes are broadcast. That's the equivalent of putting flyers everywhere or putting your advertising services on each one, but the reads are local. Okay, so then I'm only going to read my local one and I find it. Okay, that's one approach. Okay, the other approach is writes are local, which means that I want to post a flyer, I just go to the nearest one and say I'm selling my furniture. I don't post it on anything else. Okay, in this case, when a user needs to look for something, they have to go and look for all bulletin boards to see, because each one has a different set of data. Okay, so your writes are local, but reads essentially have to go and query all of these copies of the bullet. So you'll see that in that case, the write was done just in the middle one. Okay, so when some application is reading it, you're going to go and read all of it. Okay, so both of these are possible in this bulletin board architecture because a distributed bulletin board, okay, you can use replication, or you can essentially keep a copy on any one of them and then ask for matches on all of the bulletin boards. Okay, so this is a very quick overview of a distributed coordination based middleware. Okay, not something that you probably have used in this class or previously, but it is a model that is used for certain types of application. The most common use case is service discovery. Okay, that is one place where it has become popular. In IT environments, you essentially have all kinds of services that are being broadcast. You can go discover them on the fly. Okay, and many operating systems have service discovery built in. So Mac OS has something called Rendezvous. Okay, so you can have it now called Bonjour. So you can essentially open a browser and say what Bonjour services are available. It will go find all of them that are in the environment. Okay, so you can, for example, use it to share your iTunes library on your Wi-Fi network. Other Macs can see it. Okay, that is how they know that there is one, because it's advertising itself in the environment. Okay, so this is how you are going to advertise services and look for services. Okay, any questions on this before we move on to distributed data processing? Okay. Yes. Okay, question is, why are there multiple copies of A and B, right? So this is a logical board, right? The physical realization of this board looks like this, right? So in this case, each write is broadcast to all copies, right? So if I want to write A, or put a note saying A, I'm going to put a note on this bulletin board, that bulletin board, and that bulletin. So now there are 3 copies of A actually present in the system. Okay, this is the logical view. This is like the union of all the notices across all my bulletin boards. So you posted the flyer 3 times, so that's why there are 3 copies. That's all it's right? Anything else? All right, so we'll talk now about distributed data processing. Okay, so this is a much longer topic you might encounter in other classes if you've taken systems 500 level systems courses. To go into a lot more detail there, but I do want to mention this briefly here for those of you who may not have taken these classes. So I'll talk a little bit about what these systems do, and we are going to look at 2, map, reduce, and Spark. Okay. So what are big data applications? So these are applications that are trying to process very large data sets. Okay. These could be scientific applications that are going and processing maybe satellite data, or it could be all other kinds of genomic data, as you can see, image data sets, or this could be very large amounts of financial data. In the medical field, you might have all kinds of large repositories. So you're using it to build, maybe look for new cures for diseases. So whatever the reason may be, there are many domains where there is increasingly very large amount of data sets. Okay? And there are applications that want to process it for some reason or the other. Okay? Now, the same example is also true for machine learning training, okay? Where you're training a model on a large data set. But that's just one example. Okay? And there have been all these big data applications that have been there for decades. Okay? Process lots of satellite images, process medical data. You're not trying to learn any necessarily an AI model there, but you're using it to do other kinds of processing, right? Genomics and things of that. So then because there are many different scenarios where you want to process large-scale data, one question is, how am I going to build a platform that allows me to systematically process very large amounts of data in parallel? Okay? One way is you are going to essentially have your code run on one machine. That machine is simply going to read some part of the data, process it, read some other part of the data, process it. But since you're only one machine doing this, it's going to take you a very long time to process a large data set. Okay? So you want to parallelize the processing. Okay? You want to now use a cluster of machines that are going to process this data set, parts of this data set in parallel, so you can go through that entire data set faster. So what's a good way to do this, right? So that's essentially the topic for big data processing or distributed data processing. Okay? So let's look at two different approaches for doing this. Okay? One is called MapReduce. Okay, I don't know how many of you used it or actually know about it, but this is a way by which you can take a large-scale data set and process it in two phases. Phase one is called map. Phase two is called reduce. Okay? So you will see here that you have essentially the top row, the top boxes represent the map phase. So initially you have a large data set. In the map phase, you start reading that data, do some processing. Okay? And then that intermediate results of that processing are sent to the next phase called reduce phase. Okay? In the reduce phase, you see that there is something called a shuffle where the intermediate results are then sent to one or more nodes that are essentially doing the final stage of the process. So map is the first phase and the reduce is the second phase. Okay? So you do the first level of processing, generate intermediate results. You then send it to whichever node needs it. That's essentially the shuffle. And in the last phase, you are going to then do the final processing, and the blue boxes are essentially your final output. Okay? So this is a way by which you can write applications. So if you want to use the MapReduce model, you got to take your scientific application that needs to process any type of data and then split it into a map phase and a reduce phase. And the middleware is then going to take the code in the map phase and do this. It will then essentially take your large data set, chop it up into chunks, read each chunk, essentially run the map code that then basically it processes that data and produces some intermediate result and so on. And those intermediate results are then sent to the next phase for processing. Okay? Is that clear what I just said? So let's take an example. Okay? Let's say that you want to take a large set of documents and then you want to do word counting. Okay, so all of you know what word count. That's a very common example for MapReduce. Right? So how are we going to do this? Right? So let's say that you take, let's say it's a book, right? So you take each page of the book, that's a chunk, and then you give it to each of these machines. Okay? So it's going to read this page and you look at the words, and then it's going to say, I found this word. So the count is 1, I found another word. So maybe in this page you have 5 occurrences of this word, 3 occurrences of some other word, and so on. Okay? So that is what each of this machine is going to do. So you have processed now each part of that document in parallel and found the number of word occurrences. Right? So now how are we going to then find the final word count? What do we do? You have to sum everything up. So let's say there is the word program. Okay, that it occurs 5 times here and 7 times here and 2 times here. You have to essentially then merge all of them, right? So what you're going to do in the reduce phase is you're going to assign one node for each word. Okay, each word is mapped to one of the nodes. So the intermediate results are going to send to the right node. So if the word program may be now assigned to node 2, so anyone that has seen that word and has a partial count has to send all of those results here, and then you sum them up. Then you know how many times that specific word occurred. Okay? For some other word, maybe you say that is the node that's responsible for it. So each of those nodes, when they see that occurrence of the word, send their partial results here, you sum it up. Okay? And at the end of this process, for every word, you found a total number of occurrences in a large document. Okay? And you're doing all of this in parallel rather than scanning the document and doing this sequentially, because there could be a large number of map nodes, large number of reduced nodes. Is that clear? Very simple idea. Now, the goal is that you have to take any algorithm for doing scientific data processing, and you have to convert that into a map and a reduce phase for it to work on this platform. The platform fundamentally says you have to write your code as a map reduce program. Okay? And then the system will parallelize it for. Okay? You can't take any arbitrary code and run it here, because this platform expects that your data processing code is written as a map and a reduce program. Okay? The mappers run the map part of the code, the reducers run the reduce part of the code. In the shuffle, you are essentially sending intermediate results from the map phase to the reduce phase. Is this clear? Okay. All right. So that is our map reduce program. Okay. Now that's just one of the many distributed data processing models. There are many others which I'm just going to mention. We are not going to go into this. There are essentially the Microsoft DIRAD and NET. You can think of the entire data processing task as not 2 phases, but many phases that are a directed acyclic graph. Okay? This is just saying my processing is split into 2. There's phase 1 and phase 2, and I'm exchanging data. But why stop there? Why not say the processing is n phases? Each phase produces some arbitrary intermediate results. They can be sent to multiple intermediate phases. You can merge the results, do all kinds of more sophisticated processing. Okay? So if you have that type of model, you can essentially use this other framework that say map reduce might be too simplistic. My code requires more than 2 phases. So I'm going to now write it as a multi-phase distributed data processing program. For that, you have other platforms like DIRAD and NET that do this type of processing. Okay? And we are going to look at another one called Spark in just a moment, but I just wanted to see if this was clear. Any questions on this? Okay. So the Hadoop big data platform has many different components. We already saw one of them before. That was HDFS. Okay, I talked about that at the beginning of the class. That's the file system that's going to store our data sets. Okay? So HDFS is the file system that stores our data sets. Then you have compute nodes that are essentially either mappers or reducers. The mappers are going to read from HDFS, okay? Process data. They can then send that to reducers, or the intermediate results can actually be written back to HDFS, and reducers can read from HDFS, process it, and produce end result. Okay? So both of those options are possible. So you have HDFS as the file system. If you want a more database-like framework, you use HBase. You can use things like Kafka and so on. Okay? So, and when we were doing cluster scheduling, you may remember we talked about Mesos. Okay? Said it was a 2-level scheduler. So if you have map reduce, you can plug that into Mesos, and Mesos will allocate resources for running your map reduce task and so on. Okay? If you remember, when we talked about Borg and Mesos, we said you have 2-level cluster scheduler. The top level allocates machines to frameworks, and the frameworks run the map jobs. In this case, they're map reduce jobs. Okay? So this ecosystem has many different components, and we have just looked at 2 or 3 of them, but there are many others. Yes, question. Okay. Question is, how is HBase using map reduce? So that's just a storage layer. Okay. So in this case, our mappers and reducers have to either read from whatever storage layer is present. So in HDFS, you're reading from a file system. In HBase, you're reading it from the HBase. Okay, that's all. Okay, so here is a picture of all of them. So the bottom layer is our storage layer. As I said, HDFS, HBase, there could be others. The middle layer is the resource manager. We already saw Mesos. Yarn is Apache's open source framework that looks very similar like Mesos. Then your data processing framework, you only seen one that was MapReduce, but there are a whole bunch of others that allow other models. We'll look at Spark in just a moment. And then there are higher level applications that give you higher level abstractions to write code to use this framework. Okay? So quite a complicated middleware system for large scale data processing that spans from where to store the data, how to allocate machines to do the data processing, what middleware you're going to use to perform the data processing, and higher level things that allow us to write code or queries that are actually going to be sent to all of these applications. So if you want to use these, you actually have to know something about each of those layers. Okay, so and I already mentioned all of this. And machine learning frameworks are no different. Okay, they basically form a very similar hierarchy where the data, if you are using TensorFlow or PyTorch, which some of you may have used, it uses similar things, right? So their data set is stored somewhere. Normally, it would be stored on a standard file system, but it doesn't have to. It can be stored on GFS or HDFS or things of that sort. And then you might have Mesos allocate machines to run your PyTorch or TensorFlow job. And then rather than using MapReduce, you are using TensorFlow or PyTorch to do the training. Okay? And then you can have higher level applications that are essentially writing training code and invoking this framework. So ML processing is just one example of big data processing. It follows the same framework, and there are many more, which I'm not going to talk about. Instead, we'll talk a little bit about another one like MapReduce called Spark. Okay. So Spark is another big data processing platform. Okay. It has essentially evolved from MapReduce, but it tries to overcome some of the limitations of MapReduce. Okay. Now, MapReduce is designed for large-scale data processing, but it is somewhat slow because it involves doing a lot of I/O. Okay. You have to read the initial data from a file system. Okay. You do the map processing. Okay. Maybe the intermediate results of that map is another large intermediate data set. Okay. You write it back to HDFS or whatever your storage layer. And the reducers start running, they read it back from HDFS. The shuffle might actually output its data to disk rather than directly sending to map reduce task. So reducers read that data, process it, produce output, goes back to HDFS. Okay? Maybe that's going to be taken by a second map reduce task, and then this process continues. Okay? So in many cases, the throughput of map reduce task is somewhat limited by the speed of I/O that you can perform in your system. Okay? Now, Spark was designed to overcome this problem where it uses the memory on machines to store intermediate data as much as possible, rather than by default writing intermediate data to disk. Okay? That's the main innovation of Spark. This is more of what the Spark framework. So you have Spark itself. On top of Spark, you can just use standard SQL queries. You can do stream processing. You actually supports training, machine learning training, just like TensorFlow. You can use GraphX to use this as a graph database and so on. You can write your programs in Java, Scala, Python, all kinds of things. Okay? But the most important aspect that we are going to highlight and actually focus on a little bit is its in-memory data structures that are called RDDs, okay? Resilient distributed data set. Okay? So what is the notion of an RDD? So think of it as a large distributed memory system. Okay? So rather than thinking of the memory on your system as a collection of RAMs on each machine, you just think of, I have RAM on multiple machines. Okay? I just take all of their union, I get a big pool of memory. Okay? Whenever my Spark system produces intermediate data sets, I just essentially put this into this memory, and it essentially becomes what's called a resilient distributed data set, because the system is going to take care of spreading that data across multiple machines. So essentially, this is like distributed memory. Okay? Now, when my next phase runs, rather than going back to my disk and trying to fetch data, I just go to this distributed memory system, which is all in RAM, and say, give me the intermediate results. Okay? And I just read it from memory. And it may not be in my local memory because it's distributed. Some parts may be on machine 1, some parts, chunks may be on machine 2. But this gives me a unified view of RAM. So I can just say, give me this data. It will fetch it from wherever it is stored and give it to you. Okay? And that is always going to be much faster than writing data to disk and reading it, because disk I/O is slow. Okay? Local memory I/O or remote memory I/O is always going to be faster. Memory accesses are faster than disk accesses. Okay? So this is going to eliminate a lot of the overheads that MapReduce is going to see by keeping data in memory as much as possible. Okay? And the idea is machines have, if they have lots of memory, let's use that to store. Essentially, it's a cache, if you think about it. Let's use it to store our intermediate results in RAM rather than disk. But because RAM on each machine may be limited, the system is giving me a way to pool RAM across multiple machines and think of this as one big pool where I just put data. I don't care where the machine actually decides to store it. Maybe on my RAM, somebody else's RAM, that doesn't matter. The system will take care of it for us. Okay? Is that clear, what I just said? Okay. Now, of course, you have to remember that RAM is not unlimited. Okay? Your size of your distributed memory is still limited by the total size of the RAM across all of the machine. So if your data is larger than the size of distributed memory, it's still going to spill over to disk. In that case, you can't speed anything up because only some of the memory will be cached, some of the data, the rest will be on disk. Okay, so, but if you construct your programs carefully so that it can all be stored in distributed memory, your Spark data processing will run much, much faster than MapReduce. Okay? But in the limiting case where you have lots of intermediate data, it cannot be stored in RAM, it will look not very different from MapReduce because there's more disk IOs. Okay? So it's almost like you put a big cache in memory cache, and whenever you are getting data from cache, everything runs faster. But if you can't fit everything in cache, it's not going to be any worse than what you had before, which was I just wrote everything to disk and read it back. Okay? So that was essentially the big change from going from a MapReduce or Hadoop model to a Spark model where your objects cached in a RAM across a cluster, and you have this notion of a RDD that allows me to speed up my intermediate processing. Beyond that, you can still use the MapReduce programming model to write Spark program. Okay, you can have a map phase in Spark, whatever output it produces, you put it in an RDD, the reduce phase reads it, and you process data. That's still there. There are all kinds of other ways to write Spark applications as well. You can write SQL queries to an RDD, might look like a database, so you can query it. You can use it to do ML training. So all of that can be done, but you can make use of this distributed memory. Okay? And there are different forms of RDDs which you can use for narrow transform, wide transform, but I'm not going to go into those details. I can make a pointer available if you want to go read more about the Spark paper. The big concept was use distributed memory to speed up processing. That was, I think, the takeaway from Spark. Okay? We'll stop here, continue next time. We ran out of time. So